the members of our network are some universities, as Luis told for us. One of them is the Universidade Nacional Maior de São Marcos, a decana da América, em Peru. A Universidade Nacional de Colômbia, na Colômbia, claro. Universidade Nacional de Barranca, no Peru. Universidade de São Sebastião, em Chile. Universidade de Zulia, Venezuela. Cinvestap, no México. E, no Brasil, a Universidade Federal de Pernambuco e a Universidade Federal Rural do Rio de Janeiro. E também temos como colaborador todo, and also we have as collaborator every week, every Saturday, Professor Stuart Holmes from the University College of London. Alexander, so we have now, we will have 1 hour, at about 1 hour, to show your talk. Did you try your?
Yeah, I'm sure I will share my.
Yeah, sure.
I will share my screen, and yeah, sure. Can you see the?
No, it's coming. No, it's good. It's not
okay.
In the. It's not.
It's not.
It's not in the. How can I say? It's not in
presentation mode.
Presentation mode.
Yeah.
You need to put it in presentation mode, and after share with us.
Can you see when I change the slides?
Yeah.
I'm changing the slides in this. Have you seen this?
No movement.
No movement. Yeah, I have a problem. Yesterday at night, I gave a presentation, and I couldn't do it in the presentation mode because there was no movement.
But there is no problem. You can move one by one, or not.
No, if I put like that, you can see movement. Yeah.
Yeah. Yes, we can.
Yeah, because when I put in the now you can see movement or no movement. Change. It's changed or not?
No.
That is the problem. It's easier if I present like that. It's not in presentation mode, but now you can see the.
Now you can move.
And can you read the slide? It's easy. I can.
Yeah.
Okay. Sorry, but I don't know what's happening. It happened yesterday in another at night, another Zoom meeting. The same problem. I had the same issue.
Okay, there is no problem. You change it one by one.
Yeah. So let me start. And can you see the whole? There are slides. Okay. And just a moment.
No problem. Take your time.
So just a moment, please. So thank you very much for your patience and for coming here today, Saturday morning. And I will give you a brief overview on the electric power applications of superconductivity. If you are having any trouble to see the slides, if you cannot see this very well, please tell me, and if there is any issue with the slides. And okay. I work in the electric power research center. In Brazil, it's the main electric power research center in the South America. And we have the largest laboratories for high voltage and short circuit tests and other labs. And I will give you today just an overview on applications. It's more conceptual. It's not theory or not basic science. But if you want later, I may suggest some names, some other presenters that could give some more details of these applications and some works in Brazil. But I will give you a panorama, an overview of the main applications and projects in the world for the electric power applications only. And so, can you see now is outline? Change it. Isaias, are you seeing the outline?
Yes,
okay.
Yes, you can see it.
Okay, so I started a brief overview about superconductors. You know this very well, and superconducting materials for power applications. And talk a little bit about magnets. And so this is the core of the presentation: power applications and fusion reactors. I separate fusion reactors because it's something special regarding power applications. Oh, everybody knows that in order to have superconductivity, you need to respect these three critical parameters. And therefore, all applications, you need to optimize these parameters. It's not only temperature, but also the current density or critical current and critical field. And as you can see, they are correlated. So if you're not inside this volume in blue, it's not superconductor. And applications, power applications, and most applications use type 2 superconductors. It's easy to understand because you can see that normally type 1 have very low critical fields as compared to type 2. And normally we operate when we use an application, a superconductor device or equipment, we are operating between the BC1 and BC2. And this is for an niobium thing, but BC2 for high temperature superconductors are much higher. And as you know, type 2 superconductors, you have in this region, you have a mixture of normal and superconducting regions. And you have the flux, the vortex. And what happens, it's very important for applications, especially for AC, alternate current applications. Every time you have a variation in the the magnetic field, I mean, if you have a variation in the magnetic field, you generate electric potential. That means, in other words, you have to prevent the movement of the flux inside the superconducting region because it causes energy dissipation. And this is really critical for attaining high critical currents in superconducting materials. And how to prevent it? By using defects or non-superconducting inclusions particles. Typically, you know very well, you may know that these vortex, they have a nanometer scale. So this is the case of high temperature superconductors, but it happens also in low temperature superconductors. You need either nanometric particles or defects to pin to achieve the flux pinning. And they can be ex situ, they can be introduced in your material or generated during the processing. And this is just a comparison of two kinds of the morphology of particles. These particles are not superconducting, and so the flux will be trapped in these particles. An homogeneous distribution of particles with a suitable size is needed, and it is the main way of achieving high currents under high fields. The morphology also of the particles has a big influence. If you have either spherical particles or columnar defects, there is a lot of difference in the interaction between vortex and the particles, and some of you are experts in this field and may understand this very well. And here, the evolution of superconductor materials, and most of electric power applications. Sorry, there is any question? So you can see that we had a slow increase along the decades of the critical temperature, but since the 80s, we have the discovery of the so-called high-temperature superconductors, all these in red, and also magnesium diboride, that's not exactly high-temperature superconductor. And we surpassed the liquid nitrogen temperature. And it was amazing because there is a big difference between using liquid helium or liquid nitrogen, because liquid helium is much more expensive and not so abundant as liquid nitrogen. In the middle, you have also here is liquid hydrogen, and but not, as you can see, I will show you, not all applications can use liquid nitrogen because it depends on the magnetic field, because the critical current is a function of magnetic field. If the magnetic field is higher, you need to reduce the operational temperature. Sorry, some slides are in Portuguese, but these are materials for superconductors for applications. And there are plenty of superconductor materials, but really few materials are good for applications. And for our applications, you need very good performance and a certain magnetic field. And the magnetic field, it will depend of each application. Some applications require low magnetic field, and others have high magnetic fields. And low temperature superconductors are the niobium-based ones, mainly these two, niobium titanium, niobium tin. And niobium titanium is the most commercial one, and nowadays also niobium tin, because when you need to attain higher critical fields, high fields, you need niobium tin instead of niobium titanium. All of these are commercial, fully commercial, but you need liquid helium to cool these materials. So, for most of the power applications, we use either high-temperature superconductors or magnesium diboride is a promising material, is in the middle. Magnesium diboride, you can see it has about 39 Kelvin TC. It's not exactly a high-temperature superconductor. Some physicists, some people consider this as a low-temperature superconductor with but what is the difference? That when you have magnesium diboride, you cannot use liquid nitrogen. Liquid nitrogen is 77 Kelvin, but you may use gaseous helium gas. And there is a big difference between using helium gas and liquid helium, because of the energy you need to liquefy helium is much higher than that for having helium in the gas form. And these are the main, these three ones are the main high temperature superconductors for applications, the bismuth compounds and the YBCO compounds. And nowadays, the YBCO compounds are becoming already industrial. And BISCO, the bismuth compounds, were the first generation that become the industrial, firstly, mainly fabricated by Sumitomo and a Chinese company. And now, nowadays, we have many companies producing the YBCO. That's nowadays the most important one for electric power applications. Here's some examples of superconductor wires. You can see either niobium-based low-temperature superconductors, magnesium diboride, and BISCO-based wire, and rare earth IBCO-coated conductor. And you can see that all these materials have metallic matrix, non-superconducting matrix with a multifilamentary architecture, where each filament is superconducting. However, when you have the BISCO, the high TC, normally they are highly anisotropic, and in general, you need to use it in this flat tape form. BISCO-based 2212 can be done, is also anisotropic, but it can be done in round wires. There's a special way to do it. And magnesium diboride is not anisotropic, and it can be done in round wires. Round wires are preferred by the industry and to making coils, etc. But because of anisotropy in general, we need, in case of these two materials below, you need tapes. And some other pictures of, you can see here, the YBCO second generation tapes that are the most important materials for power applications nowadays. And there's well-known bulk materials, the BISCO, bismuth, first generation wires, and the bismuth bulkos as well. And what's the main interest for using superconductors in power applications? Of course, you can reduce the loss, but on the other side, you need some power to cool down the superconductor. Even so, you have some efficiency gains, but in many times, the main advantage is this one. Is the very high critical, the very high current density you can achieve with superconductors. This is a comparison that's typically copper wires used for cables and coils for machines or equipments have typically 200 amps for square centimeters, whereas typical superconductors for applications can achieve general density. This is not the superconductor density. This is density considering all the material, because you see here, you have a cap, coating, a metallic coating. The superconductor is just a part of the material, as I told you. If you consider the whole cross-section, you can achieve, even so, you can achieve tenths of kiloamps. So you have 100, 200 times more current density. It means you can have much more compact and lighter equipments and device, and it brings a lot of advantages. However, as I told you, these high temperature superconductors are very anisotropic, and the current density is a function of the direction. You will need to align the alignment, the texturization of the material. You have the weak links. Nowadays, the second generation tapes, this problem has been overcome, but the weak links used to be a big problem high temperature superconductors, but nowadays it has been mitigated. It's the problem that the critical current or the critical between the intergranular critical current is much lower than the intragranular critical current. So we need connectivity, high connectivity, and densification of the material. And here you have the main high temperature superconducting compounds. But as I told you before, the yttrium and bismuth based ones are the most interesting for power applications, and the visco are nowadays called as first generation wire and YBCO second generation wire. And what's the difference? That's the YBCO wire and visco wire. Both have good properties and very high JC. It is the typical crystal structure of YBCO, as well known. It's a defective perovskite. And it is another important thing. The current, as I told you, the current is anisotropic because it flows mainly through these copper oxygen planes in the crystals. And so you have to align the grains in this direction. And these formulas are not really stoichiometric. And you can see, can you see a small delta here? You have deviations from stoichiometry, and small deviations from stoichiometry cause a lot of difference in the final critical temperature. For example, this is just an example of, it's not superconductor, perovskite, but these are perovskite-based materials. You can see what happens if you change the oxygen content. You can see the same material, the color, and the aspect can change totally because of the oxygen content. And here, what happens, for example, with a typical bismuth 2212 compound, you can see here oxygen stoichiometry, slight difference in the content, oxygen content plays a big role in the TC value, as you can see here. And so it depends on optimal processing conditions to achieve the highest TC as possible. Weak links, as I said, in polycrystalline materials used to limit critical currents because of the it's kind of a bottleneck because of a JC in the grain boundaries used to be much lower than the inside the grains, and this was a big problem, but has been nowadays it's much more optimized, and it's not still so challenging. The process, the processing methods have really progressed a lot to overcome or at least reduce the weak link effect. But if you don't have a very optimized and controlled process, you have such problem. And this is just to show you how anisotropic such materials can be. And you need this section of first generation tape that we produced once at CEPEL, and you can see a longitudinal picture, and you need the grains aligned in the current flow direction. And here the example of the one grade, there are plate-like grains with a high aspect ratio or high anisotropic morphology. And this is just to show how complex are the phase equilibrium of such materials. And I studied my PhD thesis, and just to give you a picture and how complex it is, and how the process must be really strain controlled. And here's the architecture of a typical second generation YBCO tape. It's very different from the others, as I told you. I showed you that most of superconducting wires have a conventional metallic matrix with filaments of superconductor. However, in the case of YBCO, you have a multi-layer architecture. It's analogous, similar to semiconductor compounds. And you use normally processing techniques that are adapted, that are basically similar processing techniques that were once used for producing semiconductor materials. However, the big difference is when you make a semiconductor material, like a silicon wafer, you don't need a kilometer. It's not that big. The big challenge here is that you need to make very long tapes, kilometers length tapes using coating methods, deposition methods. Oh, here is a comparison. Why I'm talking a lot of second generation tapes? Because as compared to first generation and to all other superconductors, even the low TC and MgB2, YBCO is the material that has the best behavior under high magnetic fields. You can see here the critical current. Normally it decreases with increasing magnetic field, but you can compare. You can see that this decrease is not so fast in YBCO as in BISCO-based superconductor. And this was at a liquid nitrogen temperature. If you have liquid helium temperature or lower temperatures or liquid helium gas or another cooling method, you can have even better performance. And here, just to show you the multi-layer architecture, you have a substrate, buffer layers, and the rare earth, and that's not yttrium. You may use another rare earth elements and a cap layer to protect and stabilize the superconductors. Can be made by copper, or you can have, and you have a conductive silver layer between the copper and the small thin films. It's a multi-layer of thin films, and you see that it's typically 100 microns wide. This width, is typical 100 microns, but the superconducting film is typically 1 micron or a few microns. The width, it's typically a few microns, and so it's typically 1% or few percent of the whole cross section. This here you can see what I said here. This is the superconductor layer, and you have the buffer layers and the substrate and the cap layer and the silver layer. And nowadays we have about 10 companies producing superconducting second generation wise in the world, and it is very interesting because you can see 2006 on these two were manufacturing superconductors. Nowadays we have 10 companies in many countries, and manufacturing the production, the volume production per year has been increasing. It is just from Superox, just from one of that companies, has been increasing a lot because of demand. Demand is not only for power applications, but for many magnets and other applications. And demand drives capacity scale up, and the economies of scale bring the price down, because the big problem is that these tapes are still quite expensive. You can see here that the price dropped a lot along the years, but it's still expensive for commercial applications. As you can see here nowadays, the price of a rebaco is typical. This price is by kiloampere and meter. It's not on the price per meter. We have to consider the price per kiloampere, because you are considering the high current density current capacity. And magnet superconductors, superconductor magnets, are the main drivers of applied superconductivity, because of for high fields, you generally don't have an option. If you have very high fields, you need superconductors that are typical niobium-based superconductors, because the conventional electromagnets, you have both loss, high Joule loss, and also you have the saturation of the core. The magnet core saturates, and that's why you need superconducting magnets for high field applications. This is the main commercial application of superconductors. It's quite common nowadays. Is the magnetic resonance imaging. You can see it's easy to understand why, because of if you use a copper magnet, you need a huge power amount per unit, and they reduce the power amount per unit, and this is very important, and this makes this pays off. This makes the use of superconductors much more interesting for magnetic resonance. There are other advantages, of course, also in resolution, image, and performance, etc. And particle accelerators, you know that they need a lot of magnets as well, and they demand tons of high-quality superconductors, not only magnets, but also superconducting cables. Yeah, just to see just one solenoid of the old LHC, the Large Collider, you can see the size of this, and it was not the biggest one. The biggest one was the Atlas, is much higher, and you can have currents of tenths of kiloamps in the current feeders and the magnets. Here's another example of a completely different example, just to show you it's interesting field where you need also very high currents. Is industrial application. This is the first industrial application of a superconductor. Is the use of bus bars. This is short bus bars of some tenths of meters or hundreds of meters, but in some in industries, you need very high current, for example, in chlorine production and aluminum production. And this was developed by the Karlsruhe Institute of Technology. There's 3S component are installed in an industry for chlorine production, I think. And nowadays, in this project, they achieved 20 kiloamps in the superconducting bus bar. And the superconducting bus bar is much more compact than the copper bus bar. In just 25 meters, you don't need for these applications long lengths. It's very nice. It's easier to make it in small lengths. Nowadays, they have another project where they are going to achieve 200 kiloamperes in a bus bar. This is amazing. And remember, this kind of DC application, as I told you before, we have AC and DC. In DC applications, you have no losses in the superconductor. But in AC applications, you have some losses because of the movement of the flux of the magnetic flux or magnetic vortex. These losses, of course, are not so high as in the copper wires, but they must be controlled not only because of efficiency, but because this loss also they heat the superconductor. You demand more cooling power because of AC losses. But in this case, if you have a DC applications are very nice because you don't have this problem. And here I will give you a short overview of the main electric power applications. This is a technical readiness level scale that measures the maturity of any technology. And high TRL means that we have almost a product. And you can see here are the main, I will increase here, you can see now, you have the main applications. In general, cables and fault current limiters, mainly the resistive type 1, and the motors and generators have been the most successful applications for the power sector. Superconductor magnetic energy storage equipments were very promising, but for certain reasons, including costs and other problems, I mean, nowadays there are few projects in SMEs, and it's not going to be commercial, at least in the short or medium term. And as you know, when you talk about electric power grid, you have generation, transmission, distribution. And nowadays, the so-called distributed generation that is changing a lot. the topology of the grids and renewables, etc. And new technologies are more and more important because of these changes in the power grids. And this may be the moment to introduce new technologies like superconducting equipments and devices. As I told you, the power density and the current density is a very important thing. And I will start with superconducting cables. There are many projects in the world. And what are the advantages? Higher transmission capacity at lower voltage. Is that yes?
Alexander, we have 20 minutes more.
Okay. 20 minutes. Okay. Thank you. You have higher transmission capacity at lower voltage. So you avoid high voltage equipment in urban areas. And they will have high transmission capacity at lower diameter, and free phase in one cable up to high. It's possible to put the free phase in just one cable. It depends on the geometry, on the architecture, and you have less environment problems than conventional underground cables. Of course, we are talking about underground cables because they need the cooling system. You can see here a comparison between a superconductor cable, conventional underground cables, and conventional overhead line. And it's very important because you can save space. And as you can see, it's very critical for urban areas. This is probably the highest voltage cable already developed in a pilot scale in China. This has been tested in China. It's in transmission level. And this is the longest pilot cable existent in the world, the so-called Empire City project in Germany. This is 1 kilometer cable and transmitting at 10 kilovolts, I mean, above 2 kiloamps, and it substitutes, if you had here a conventional cable, you would need 100 kilovolts. It means by using such a cable, you can save one substation. And this can justify the use of superconductor. The Superlink project is a really ambitious project to make the longest superconducting cable ever done, with over 12 kilometers, with a high voltage transmission cable in Munich. And it's being undertaken. They are still doing the first small scale prototype. Here is the first prototype of the Superlink project. It will have, I think, 200 meters to test the technology configuration. Superconducting cables can have a lot of configurations. And you can see here the flow of liquid helium. Superconducting cables normally use superconductive helium as a coolant. It's another ambitious project in St. Petersburg in Russia to achieve 2,500 kilometers with high temperature superconducting cable connecting two substations. These cables are AC cables, and they have AC losses, as I told you. In this case, the AC loss is less than 0.5 watts per meter. That's a very nice value, because the use normally AC losses can be higher than this. However, in the case of DC cables, you don't have this AC loss, but in order to use DC cables, you need to use much longer. You need much longer cables, much longer lengths, and as you can see, the best path is the main project to make. It aims to make. There will be probably a DC network in Europe, made by using conventional cables, and superconducting cables can also be used in this grid. Short circuits are also a big problem for the electrical grid, and sometimes the protection device, the conventional protection device, are not able to prevent damage like that ones you are seeing. And so fault current limiters are also a very promising application. Here I'm just showing you the most simple and most common one. There are also other kinds of fault current limiters. The idea is that if you have a superconductor in series with the line, in line with the grid, during the normal operation, the impedance is very low, it's negligible. And when you have a short circuit, it quenches. And in milliseconds, you have a transition from superconductor to a resistive material. What happens is this. The red curve shows the short circuit without the fault current limiter. In the blue curve, you can see what happens when you have a fault current limiter. And it's very nice because you have here a circuit breaker, but it will protect the circuit breaker, because if the red curve is above the circuit break capacity, this will happen. So this idea of fault current limiters is, if the short circuits are increasing in many places, and you don't have to substitute or recapacitate the road substation, you can use a fault current limiter. These were some tests we done in CEPEL with some bulk components. Also, we did it with tapes, and limiting fault currents in liquid nitrogen. This is one of the biggest fault current limiters exist in the world. There is one in China of this size, one or two in China of this size, and this one in Russia, in Moscow, 220 kilovolts. And you can see here the three cryostats. Each phase is one inserted in one cryostat. And the idea is that, just a moment, please. So, can you hear me?
Yes, we can hear you.
Yeah, go ahead. Yes.
Here is just to show you how it is installed in parallel. Here you have an air core reactor. That's a conventional fault current limiter. They put the superconductor limiter in parallel with the air core reactor, because if you have a problem with the superconductor, you can use the air core reactor as a fault current limiter. And some tests, you can see the red curve without the fault current limiter, and the limitation is amazing, the limitation of the fault current using the superconducting fault current limiter. And also voltage tests, high voltage tests to test the insulations, another critical point. All equipments for high voltage require high voltage tests to test, because the insulation is critical. If you don't have a good insulation, and insulation for cryogen temperatures, it won't work. These are the main field tests of resistive type SFF. As I told you, there are other kinds of fault currents. limiters. But nowadays, resistive ones tends to be dominant. But you may have inductive ones as well. Most of them are medium voltage level, but we have a few already at the transmission voltage level, I mean above 100 kV. The rotating machines is another, how many time I have, Isaias? How much time I have?
You have 10 minutes.
Oh, okay. Rotating machines had a quite very promising area for application. There is a lot of different topologies of rotating materials. Synchronous superconducting materials, the most common, but you may have inductive ones and hysteresis one also. But just to show you how the superconductors, this P is power. Power is dependent of the magnetic field on the current density and on the other factors. And if you can increase with superconductors, you can increase the magnetic field because you can have a much more dense magnetic field because of the high current densities. And so you can have higher current density, higher magnetic field, and partial or complete removal of iron core. And you can increase torque and power density, reduce size and weight, and lower wire resistance. Rotating machines have advantages only above a certain critical size, your rating, and you have improved thermal properties. For second, if you use second generation, as I told you, have much improved in field critical current density. Here is some examples of famous prototypes, large-scale prototypes of rotating machines. I mean, rotating either motors and generators. And here is the largest superconducting motor ever built. It was sponsored by the US Navy, and they reached more than 36 megawatts. You can compare here. The small one is the superconducting motor, and the bigger one is conventional motor. It's for a ship, for example, for transportation. It plays a big role because you have a lighter motor. And also, wind generators is another interesting field because it's quite challenging to achieve powers above 10 megawatts per wind generator. Typical commercial wind generators have a few megawatts of power, 2, 3, or a few megawatts. And if you have a superconducting generator, it's much lighter, and it's easier to have the structure. You have a lighter structure of the same size of the small power conventional one. You can increase the power without increasing the wind generator. Here's the first real scale wind generator, superconducting wind generator installed in the world in Denmark. 3.6 megawatts is operated in the coast of Denmark. It is a very interesting project, the Echo Swing project. Electric aircraft is another, is a future and interesting applications. You can use electric motors, superconducting. You can use electric motors in aircraft to reduce emissions, and these electric motors may be superconducting. That also is still main challenge to achieve rotating machines because of the costs of the wires, design issues, reduce the AC losses. In case of motors, it it's very critical because in the case of motors and generators, you have higher fields than in cables and fault current limiters, and etc. Transformers, superconducting transformers, another interesting thing because you can see here a comparison between a conventional transformer and the smaller one, a superconducting transformer. Again, it's quite interesting, for example, for transportation, because you save space and you save and it's lighter, but it has a lot of advantages. But however, nowadays the progress in this area is not that big because of there were a lot of problems that are not yet resolved, as the AC losses, and you have to recover after short circuit under load. You cannot disconnect it after the short circuit. And you have a temperature rise and have to cool down under load. It's really a challenge. Energy storage with flywheels and SMAS used to be also promising application, but it didn't become commercial for some issues. And finally, the fusion reactors are very promising application, and they may push forward because the demand of material is higher. Nowadays, most of fusion reactors are done using low temperature superconductors. But here is a nuclear fusion reactor, and with the fusion energy, you can generate steam for a conventional steam turbine. And ITER is the most famous, largest fusion reactor in the world. It uses magnetic superconductors to confine the plasma. But there are other reactors in the world. However, in many US, there are some projects for using high temperature superconductor compact reactors. Why being compact? Because of the, here, the behavior under high magnetic fields is better than as compared to low TC, low temperature superconductors. So you could make compact reactors. And projects for making compact the reactors using high temperature superconductors will demand a lot of material. And what may happen is that you can increase the scale of production of high TC superconductors. Here are the main fusion projects in the world, and I'm not showing here, but in the US they are developing these so-called compact reactors. Conclusions: high temperature wise are already produced industrial scale, but costs is still high. Real scale equipments and devices have been demonstrated successfully worldwide. The most relevant examples have been presented in this talk. Other projects are being undertaken in many countries, or at least heavily relevant examples are present. It's not exhaustive. There are many other projects in the world. Main challenges are the wide prices. It's still high, and the cooling systems cost reductions. Also, introduce cryogen systems in the grid is something that the utilities don't like very much because of operation and maintenance issues. You need very well-trained people, experts to do it. You have to reduce AC losses or scale up DC applications. Fusion reactors and particle, this is quite important. Fusion reactors and particle accelerators may push forward large-scale production, cost reduction of high temperature-wise because of the demand. This happened in the past, if you remember, with the niobium base at this low temperature-wise. The increased demand and increased scale production, it was due mainly these applications and magnetic resonance imaging. And the questions I put in red. Could you have, nowadays, most of power applications in Latin America are in lab scale, in bench scale, small or medium scale. Could you have large-scale pilot projects in Latin America? It would be very nice. And for this, we would need a cooperation among Latin America countries. It would be quite interesting to achieve this goal, because most of these projects I showed you involve more than one country, involves several countries and several companies, even Europe and the US. Thank you very much. Here is my email. You can contact me anytime if you have any further question. And I thank you very much for your patience and your attention. Thank you.
Thank you, Alexander. Thank you very much for accepting the invite, and thank you so much for your excellent talk. Now, we do the section of questions. I will call the first professor to ask you, Professor Albino, because he has another appointment after our talk. So, Albino, it's your time.
Thank you, Isaías. Good
Hi, Albino.
morning,
Nice to see you.
Alexander.
Please don't make very hard questions.
Don't
I know
worry. I work with low
I'm joking.
temperature superconductors, so will be low.
Sorry?
I
Yeah.
work with low temperature superconductor at the moment.
Oh,
So
yeah.
the intensity, the density of the current will be low. But thank you very much for your talk. Congratulations for very nice. You cover all the application, almost all the application. I think we should thank you for this talk. I have many questions, Alex. Some of them you already answered in your last transparency or slide. Sorry, because we old guys, we use the transparency, not slides. So still talking transparency.
I use it transparency also. Yeah, I use it. I remember.
Yeah, but okay. My question is, two questions. First, are there any fusion projects in Brazil using high TC superconductor? Do you know if?
I mean, huge. I mean, large project. You mean?
Yeah, for fusion.
For fusion.
Yes.
Oh, that is a good question, Albino. I learned there are 3 projects, but I'm not. I have to look for more information. I really don't know, don't have the details. I think, but they are not large ones. I think they are small scale ones. What's interesting, one is in the University of São Paulo, one is in Espírito Santo, and the one I'm not sure if I think it's 2 are in São Paulo and 1 in Espírito Santo, I think. I have to look. And yesterday I sent a message to Professor Ricardo Galvão, the famous physician. I found that he's involved in one of these projects, but he's very busy now of the transition government. And I think he hadn't time to answer me in due time. But if I found some more information on Brazilian projects, I can send you.
I would appreciate this. The second is Brazil has about 98% of niobium ore. Yeah,
Yeah.
Almost everything is here, and it's disappearing. But this is another discussion. Yeah. The
Yeah.
use of high TC. Do you think that soon, I mean, in 100 years, the use of high TC for power application, electric power application, will kill Brazilian industry, Brazilian
No,
niobium industry?
I really don't believe. I think there will still be plenty of room for low temperature superconductors. And at least in the medium term or even long term, you don't kill the industry. High temperature superconductors are very promising, but since almost 20 years, we couldn't achieve reasonable costs as we have for low temperature superconductors. I don't think it will kill the both industries will exist. And in some applications, as in particle accelerators, for example, you have the both materials. The magnets are made using low temperature superconductors, but the current leads and cables use the high temperature superconductors. And sometimes you can even combine both. And I think there are a lot of time to use niobium and a lot of applications to use niobium. But for electric power sector, niobium is very hard. It's not acceptable to use liquid helium. It is the case. But the other applications like magnetic resonance and fusion, etc., you can use liquid helium. It's not a big issue.
Yeah, liquid helium is really a problem nowadays. We should try to find any helium mine in Brazil. Otherwise,
I think this the main thread, the most main problem is not for low temperature superconductors are not the high temperature superconductors, but the lack of liquid helium. I think this is the main problem. If you don't have enough liquid helium, this is really a problem for maybe for low temperature superconductors, more than the high temperature superconductors. Yeah.
So, Alexander, thank you. I have just a small question, Isaias.
Okay.
Alexander,
Okay.
can you
go ahead.
Share with us your transparencies? I would be glad if you can do this.
No, the transparency. Transparency I don't have, but I have slides. I can
slides,
share.
Yeah, okay. Please,
Polasek, you can send your slides for me, and I can share with the LAFMAT.
Yeah, I can share with you, but some source of some information are lacking here. I have to put the source of the guys that provided me a lot of things, and I have to put some further information. Some reference are lacking. I have to put this reference, and then I send it to you.
Okay, thank you.
Okay, thank you very much. Congratulations for your talk, and nice seeing you. So long time ago.
Hope so.
You look great. Congratulations.
Thank you. Thank you.
Bye.
Thank you, Albino. The next question will be asked by Professor Luis Valadares, our General Secretary of the LAFMAT. Luis, go ahead.
Okay, Alexander Polasek, muito obrigado por la palestra de hoy. Estuvo muy interesante, muy bien, muy genial la palestra. Yo tenía unas preguntillas. Primero, quería saber sobre los nombres. Presentaste que hay alrededor de 8 empresas a nivel mundial que ya venden estos cables superconductores y mostraste algunas chinas, 2 chinas, empresas que ya venden cables superconductores. Y
Yeah, there are 10
sí,
companies.
sí,
Yeah, 10
sí,
companies. Yes, this in China is
two.
put in the presentation mode.
Dos en China, ¿cierto?
Yeah, it's very small. It's Shanghai, the Shanghai Superconductor Technology, and the other one is written Chinese. I cannot read, but I can look for more details if you want. Do you want the contact of these companies?
Sí, porque eu estou planeando viajar a China agora em março. Y que quiero contactar para comprar unas amostras de cables superconductores y luego hacer cierta experimentación.
Yeah, one of these companies located in Shanghai. I'm not sure if the others in Shanghai as well.
Ahí hay tres compañías en China, ¿cierto? Tres.
Oh yeah, because they're so small, I cannot read the name of all of them. But I can send you the name of these companies.
Yeah. Or cuando envíes, sería
I can send to Isaías. Isaías can send you the.
Yeah, but cuando sería genial si agrandas luego un poco antes de enviar los slides, ¿no? A Albino, sería si agrandas más esos chinos, esas empresas, sería genial para ver las empresas y tomar contacto con ellas, ¿no? Está súper interesante. Bien.
It's hard to see here. But I will send you I will send Isaías the information. Okay. Isaías, I can send you.
No, okay. I suppose increasing the slides, you can read it without problem.
Tenía otra pregunta.
For instance, in English.
Otra pregunta también, Alexander. Você mostró unos cables de bismuto que han sido feitos con powdering tube, creo, el método powdering tube.
Yeah, exactly.
Yeah. Unos cables ahí, las primeras transparencias creo que han sido, ¿no? Las primeras transparencias que muestra por ahí, exacto.
These were done using the powder in tube technology, and nowadays, I mean, they were the first high temperature wires to be produced and used in large scale. But nowadays, just a few projects, I think, you still use this kind of tapes. And there were, I think, two companies producing. The main company that produced such first generation wires is Sumitomo in Japan. And there was also one in China producing first generation wires. I'm not sure if it's still working, but they were very important in the development of applications.
Obrigado. Y la última pregunta, para pasar al resto la última pregunta. ¿O señor tiene alguna información? ¿Quiénes venden o sensor squid solo? Squid alone, only the sensor squid alone, not with a whole magnetometer, only the squid alone. Any information?
Oh, sorry. I'm really not an expert in electronics applications, but I know some experts. I can ask for this. You want only the squid alone? I mean, one squid sensor, alone. Yes. Only the sensor.
Yes, only the squid sensor, because we would like to do some experiments with only the squid sensor later on, because buying the whole magnetometer, the Dynacool, the MPMS, and so on, yes. The quantum design is so expensive, more than $1 million US, 1.5 million US dollar, depending on how brand new is that and so on. But only the squid sensor will be very nice to start to do some experiments. I know that, for example, Colombians, Professor David Landinés and Professor Jairo Roa in the National University of Colombia, they are buying the whole magnetometer Dynacool with a squid sensor, because Colombia has a lot of money, but Peru has not much money. No, but we would like to start just buying some squid sensor. Okay. Obrigado, Alexander Polasek. Obrigado.
Obrigado. De nada. De nada.
Say yes.
Okay, thank you, Luis. Alexander, the next question will be asked by Professor Stuart Holmes from University College of London. Professor Stuart.
Thank you, Professor Polasek. Very interesting talk. Thank you. I have many questions. I think you kind of answered some of my questions as you went along. But my first question is, in Grenoble in France, they have a magnet laboratory where you can use 35 Tesla. System is not a superconducting magnet, it's a so-called polyhelix electromagnet. How far would high TC magnets compete with that? Would they offer any competition yet for that level of static field? Or is it just high TC can provide some components, maybe the leads to room temperature or an inner coil or something?
Which magnet you are referring to?
The standard research high field lab in Grenoble, France, has 35 Tesla, so-called polyhelix magnet, which uses 12 megawatts of power. Now,
it's totally conventional. There is no superconductor.
Yeah, there's no superconductors. However, you can buy a 20 Tesla superconducting magnet conventional. Would high TC be able to compete with the higher fields eventually, or is it still too far away to say? What is the highest high TC magnet, highest field?
If we have DC magnets, you can these magnets for steady state field or for pulsed field?
For static field.
Static field, I mean. Static field, yeah. Oh, I didn't know about this because of in National High Magnet Laboratory in Florida, they have also a 45-1, but it's hybrid. Yeah, normally you have hybrid. It's a combination of conventional and really, I think maybe Lance Cooley or David Labares here could answer this question much better than me. But I believe that with superconductors, you save power, save energy consumption because it's a kind of a DC application. And for DC applications, you may save, like in the magnet resonance imaging. But I don't have the details. However, there is an interesting point. You may know that when you have the pulsed magnets, when you need pulsed magnets of a short duration, you use a conventional, not conventional, non-superconducting magnets, but because of the high temperature they achieve. But it's for very fast pulses. However, to my knowledge, normally for static fields, you need superconducting components. But I'm really cannot. I don't have all parameters to compare with this one from Sandia Laboratory. But I can ask. I think you know Lance or Cooley or David Labares or the guys from Florida. Oh, but maybe they will defend the superconducting magnet. But they can provide a better answer. But I can look for as a good question. And another question is important role in the case of high temperature superconductors. They play a very important role for the current leads, because you save a lot of power if you use current leads, bringing the current from the room temperature to the low temperature. And current leads with high temperature superconductors, it's I think a well-established market. Yeah.
Thank you. I've one final question, and that's to do with power transmission. Is there a figure of merit, perhaps, that superconducting cable, if it reaches that figure, it could be cost per kilometer or cost per kilometer per kilowatt? Is there a kind of a figure of merit that the high TC cables have to reach before they'll come into general use? Is it a cost or?
Oh yeah, it's a good question. Normally, they have to. A figure of merit is the compactness. Yeah. For example, the idea is that typically one underground superconducting cable is equivalent. Replaces about 3 to can transport the same current as 3 to 9 conventional copper cables. It depends. There is 3 to 9 because of, one superconducting cable is typically 3 or 9 times more, have more 3 or 9 times higher currents than one conventional cable. It is a figure of merit because if you don't have a much higher current density, it doesn't make sense. Another thing, of course, is costs. The costs will depend on which kind of voltage level you are using and the currents you are operating, the range of current. And but I think it's important thing. It's how much space you can save, and this is very important because there is important thing because you have to shield the magnetic field, the self field, or the field of one cable. It can affect the field of another cable, and this reduce the critical current. And if in this case you have to have a very optimized geometry to reduce the size. Otherwise, you have to, if because of the magnetic fields, you have to, you need more space between wires, superconducting wires, so the cable will become large, and it doesn't make sense. So you need very special guys are developing very tricky and smart geometries to make it even more and more dense. And this is a figure of merit.
Thank you. It's a complex problem.
Yeah, it's quite complex.
Complex, yeah. Thank you. That's very interesting. Thank you, Professor Polasek.
Oh, I thank you very much.
Thank you.
Thank you, Stuart, for your question. Thank you, Polasek, for your answers. And now I'll call Professor Alexei Vagov. Alexei, are you here? Alexei? Oh. Let me try another Russian physicist. Mikhail, are you here? No, we have a problem with Russian connection. Let me call another one. Arturo, are you here?
Yes.
Okay, Arturo, go ahead.
Many thanks for your excellent talk, Professor Alexei. I have a question. Are conducting cables a cost-effective technology for long transmission lines?
Sorry, could you repeat your I was seeing a message from Albino here. Sorry, could you repeat your question?
Okay. Are superconducting cables a cost-effective technology for long transmission lines?
No, not yet, because of you have two issues. Yeah, one is when you have long cables, you need much more wires, and this becomes much more expensive. And the other problem is that the longer the line, the more cooling stations. You understand that if you had 100 meters cables or 200 meter cables, you can have just one cooling stations or one cooling station on each side. But if you have 100 kilometers, 10 kilometers cable, you need the cooling stations in between to keep the temperature. So you need more cooling power. However, this is an interesting question because of, possibly you don't have, in order to use superconducting cables, you may use also short cables may be helpful. You don't necessarily need very long cables. Why? Because if in the electrogrid you have a lot of bottlenecks, you have place where you don't have space. It's mainly urban areas or where you have environmental problems, and there's so kind of right of way. The right of way is the space you have available to install overhead line. If you cannot install overhead line, you need to use underground cables. Underground cables, even conventional, are more expensive than overhead lines. But so sometimes you have in space. Even let me show again a slide. It's explain. It can just illustrate what I'm telling you. The idea is you may have a hybrid line. You can have a conventional line and a piece of that line, a short piece, a bottleneck of the line can be substituted by a superconducting cable. But you can have a conventional line and one piece of the line where you don't have space to have a bottleneck, you may put a superconducting cable. This is a good application. And let me here. As you can see here, it's clear. See, such case, in some cases you may not have space available for transmit the necessary power, necessary current you need. In such case of bottlenecks, you may use relatively short cables or a few kilometers cables. But really for long length, hundreds of kilometers cables is not cost effective. Not yet.
Okay, many thanks.
Thank you, Arthur Isaías. Your second name is very beautiful.
What? Your second name, yeah. Isaías, yeah.
Arthur Isaías. Now, the question, Professor Davi Landinês needs to left the meeting, but he has one question here. His question is, what is the current state in the production of second generation high-C superconductor in Brazil? Couldn't you understand?
No, sorry, I haven't understood. What's the question?
What is the current status in the production of second generation high-C superconductors in Brazil?
Oh, I don't know any big projects for producing second generation superconductors in Brazil. Maybe the guys in Lorena know something, but to my knowledge, there are not really, probably the status is lab scale, because we tried in the past, but the production of second generation tapes is really quite complex, much more complex than first. All superconductors are complex to be made, but the second one, as I showed you, is quite complex. and it requires a lot of special machines. And in fact, they are expensive because of the process methods. The materials are not so expensive. I mean, for example, the first generation, just a moment. The first generation bismuth-based compounds need silver. Second generation don't need so much silver. The problem is the processing is expensive.
Okay. The next person to do a question is Professora Ximena Velasquez. She's going to Cambridge. Ximena, go ahead. Ximena, are you here, Ximena? Oh, my God. Ximena.
Profe, qué pena, es que casi no lo logro.
Okay.
Yeah, I'm here.
Okay.
We only can to say thank you. We are grateful for this talk, but we don't have questions from our university.
Ximena, if possible. Okay.
We don't have questions from our university. We only can to say thank you. We are grateful for this, for the talk.
Oh, muito obrigado. Muchas gracias and thank you.
Okay.
Creo que también está el profesor Sergio Conejeros de la Universidad Católica de Antofagasta, en Chile.
Sí, we have a big list to call everyone. Sergio, it's your time now. Go ahead.
Hi, thank you, Professor Alexander, for your very nice talk and very nice example of applications. The question that I have, you have already answered, so thank you again.
Thank you very much.
Okay, Sergio. Thank you for your participation. Eliana, do you have questions? Okay, muchas gracias, Eliana. And I will try connection to Russia again. Professor Alexei Vagov, are you here? No. Okay. Luis, do you want to speak some final words for us?
Yes, muito obrigado. Alexander Polasek, muito obrigado por la excelente palestra del día de hoy. Muy excelente, estuvo muy didáctico y vimos todas las aplicaciones de los cables superconductores, etcétera, y las compañías y la comercialización que ahora está actualmente en el mercado, ¿no? Y los avances. Muy obrigado por la palestra. Y quería recordar al público, ¿no?, que nos sigue, que las siguientes palestras, ¿no? El día 17 de diciembre tenemos la última palestra del año, que estaría a cargo del profesor Carlos Santos de la Universidad de Sao Paulo. Alexander Polasek, usted está convidado de participar, si desea, el otro sábado como panelista para hacer preguntas si estima conveniente.
Thank you very much.
Sí, entonces es el sábado, entonces profesor Carlos Santos de la Universidad de Sao Paulo, en Brasil. Y el moderador, el otro sábado, sería el profesor Albino Aguiar. Luego tenemos interesantes palestras para el 2023. Vamos a tener un receso, unas vacaciones hasta enero. En enero nuevamente tomamos luego de las vacaciones, según quizá el 21 de enero, podríamos tener, no está asegurado aún, ainda, pero podríamos tener la palestra del profesor Jason Robinson, que es el Head of the Department of the Material Science in the University of Cambridge. He convidado ontem, pero va a responder la invitación más adelante, no está seguro ainda. Luego, más lo que está seguro es el día 28 de enero de 2023, la doctora Perla Cecilia Meléndez González, de la Facultad de Física, de Ciencias Químicas, disculpen, de la División de Posgrado de la Universidad Autónoma de Nuevo León, en Monterrey, México. Su palestra va a ser a catálisis heterogénea nanomateriales, caracterización electroquímica. Y el moderador será Felipe Mundaca, de la Universidad de San Sebastián, en Puerto Montt, Chile. El día 4 de febrero, ya cuando son carnavales en Brasil, 4 de febrero, habrá un fórum acerca de la situación actual en las ciencias, de la ciencia en Venezuela y las alternativas más posibles para su solución, donde van a participar especialistas de, por ejemplo, Ismar Robonal, que es el presidente de la Academia de Ciencia de Venezuela, Fermín, José Fermín, también de la Universidad de Zulia, y varios panelistas. El 11 de febrero va a dar su palestra Margarita Sánchez Domínguez, Centro de Investigación de Materiales Avanzados, en Monterrey, México. Ella va a dar tres mini charlas que serán sustratos, CERS para electrodeposición y reemplazo galvánico, síntesis de superestructuras por microemulsión bicontinuas con electrocatalizadores y sustratos CERS, y nanomedicina. El moderador también va a ser el profesor Felipe Mondaca, de la Universidad de San Sebastián, en Puerto Montt, Chile. El 18 de febrero, el profesor Durbal, de la Universidad de Sao Paulo, Isaías, ha convidado. El 25 de febrero tendríamos a la doctora Michelle Villamayor, que estuvo en Francia, y ella es filipina. Bien, luego vamos a tener otros foros acerca de la ciencia en Brasil y las expectativas del nuevo gobierno de Lula da Silva en el avance y el progreso de la ciencia en Brasil. Eso sería ya a fines de febrero o en marzo, luego de los carnavales, porque los carnavales son sagrados para los brasileiros. Bien, perfecto. Son sagrados. Muy bien, Alexander Polasek, muito obrigado. Creo que ya puede dejar de compartir sus slides, ¿no? Perfecto. Quería dar una pequeña, antes de terminar, ¿no? En primer lugar, antes de dar la palestra para para las palabras finales de despedida de Alexander, quería mencionar algo muy pequeño. Luego que termina esta sesión del día de hoy, vamos a tener por interno una palestra adicional pequeña de Ximena Velázquez y Stuart Holmes, porque estamos planeando su visita a la Universidad de Cambridge. Ya Ximena ya tiene su pasaje y tiene también toda su carta de invitación, su alojamiento y todo. Entonces va a mencionar sobre su plan de trabajo en Cambridge y en University College of London. Entonces, luego que termina esta presentación, esta reunión, entonces vamos a tener, si desean alguno de ustedes estar, no hay problemas, son bienvenidos. Más ainda es para mencionar, y vamos a continuar al final. Muy bien, Alexander Polasek, muito obrigado. Quizá você quiera dar unas palabras de despedida.
I would like to speak in Spanish. My Portuñol is really not good. I mean, I can understand the Spanish, but the Portuñol, it's better to speak in English. And also, but I will say muito obrigado, gracias, and thank you very much. Soy muito grato por vuestra atención. And thank you very much. And thank Isaias for inviting me. And as I told you by the end of my presentation, I would be very glad to, I'm already glad to see you have a network of physicists, Latin American physicists. Maybe we could have a sub-network in superconductivity, and maybe still or even a network on applied superconductivity, and just suggestions. But if you could have some more collaborations in applied superconductivity or even applied or basic science superconductivity, it would be very nice, I think, if Latin American countries could collaborate more and more. I think it's important for us all. And like the European countries do, we could do it also. And also, of course, it's not dependent only, it's not only up to us, but we may try to make efforts and push our governments to help us to do this, or the universities to make more and more exchange programs and between Latin American, not only with other countries, but between our vecinos, our friends, our hermanos. I think it's, I would be very helpful to see this, and I think this network is already a good sign that things are happening in this sense. Thank you very much.
Okay, if anyone could open your webcam,
Alexander, quizá te quería decirle alguna pequeña cosita para antes de despedir. Alexander, next, we are planning to organize the second Latin American conference on superconductivity and magnetism in Lima in October next year. It depends in this moment we are applying for funding from Concitec, and it depends, everything is on the hands now of Jairo Roa. Jairo is a Colombian who decides if the progress of the science in Peru. Well, we hope that Jairo can accept our grants. Well, if we organize the second version of the Latin American Conference on Superconductivity and Magnetism, of course you are invited to participate. Okay.
Oh, thank you very much. Thank you. I would be glad to participate in such conference. Thank you very much.
So we will open our webcam to thanks the speaker again, and so take your hand for your talk.
Thank you.
Thank you.
Thank you. Very nice talk.
Nice weekend. Bom fim de semana. É prazer ver a todos vocês. Nice to see you all, and hope to see you again. Yeah.
Your Portuguese is very well.
Okay, thank you. Thank you, Isaias. And sorry again for being late. Okay, but okay.
No, it's not a problem. Everybody could understand. Everybody has your own problems, and connection is sometimes very difficult. No problem.
Okay. Thank you very much. Nice to see you.
Okay, nice to see you, Alexander. Okay, goodbye.
Yeah, thank you.
Goodbye. Okay. Okay.
Adiós.
Bien. Okay, gracias. Bien, Stuart and Ximena están here.